Compassionate, the Merciful. In this chapter, we wanna speak about the nuclear medicine as the main chapter of medical physics course. At first, we want to know about what is the nuclear medicine and what is the important to know about it for us as a physician. Nuclear medicine is the use of radionuclide for diagnosis and treatment aims. And also with this modality, we can follow our treatment. It is also a powerful translational tool in the basic science such as biology, in drug discovery, and in preclinical medicine. And it is noticeable to know that development in nuclear medicine are driven and on the other hand are involved by advances and progression in several sciences such as physics, chemistry, computing, mathematics, pharmacology, and biology. And there is a main differences between X-ray imaging and nuclear medicine, and that is related to high contrast that we have in nuclear medicine. As you know and you learn, in X-ray, in X-ray imaging, when X-ray easily pass through the soft tissue, and we cannot see the lesion that happen in the soft tissue because in the soft tissue we haven't any contrast. But in nuclear medicine, enable us to visualize the organ and tissue as well as function. In fact, we can conclude that with nuclear medicine, we can see our tissue based on functional, and nuclear medicine provides information based on functional of the tissue and the body. And so we can conclude, we can determine the lesion that happen in the soft tissue. Due to the importance of radionuclide, as the main component of nuclear medicine, this chapter will be started with this concept. At first, I say about the main outline that we have in the nuclear medicine chapter. At the beginning, I wanna say and define the use of, and I wanna say you the main concept in physics of nuclear medicine that are including radioactive decay, half-life time, biological half-life time, and also I speak about the activity. And then we learn about the different and main particles that's emitted in the nuclear reaction that are including alpha, beta, and gamma radiation. And then I teach you about the different method of produce radionuclide, artificial radionuclide, that it is happening in nuclear reactor and in cyclotron. In the following, I also speak about the production and use of the technetium-99 as a main and common radionuclide that we use in nuclear medicine. And at the end, we speak about the different usage of radionuclide for diagnosis and therapeutic aims. Okay, let's start the first section of this chapter. As I said in the beginning, I wanna speak about the main concept of physics of nuclear medicine. At first, I wanna speak about the radionuclide. As you learn in high school, each atom consists of electron and nuclear. And the nuclear of any atom consists of a mixture of proton and neutron. The number of proton named atomic number, and that shown with caps lock Z, and the number of proton plus the number of neutron called atomic mass, that's shown with A. As you can see, A is the nuclear number or mass number, and Z is the proton number or atomic number. In practical, the nuclear can be identified by capital Z and A, and in the nature, nuclear with the same atomic number with the same Z, but different neutron number or N are called isotope. As you can see in the environment, when we have two nuclear that have the same number but different atomic mass or but different neutron number called isotope. Naturally, most elements are isotope in the environment. However, when the ratio of proton to neutron fall outside a certain range, for instance, when in an element the number of neutrons are very higher or are very lower the proton, its nuclear will be in unstable state. It is better to say in environment we have different states of the nuclear. Some of them are in unstable state. Some of them are some of them are in metastable, and other are in stable state. When the number of proton are very higher or are very lower, the number of neutron, these nuclei are in unstable state, and with decay and emission of particles and photon ray can be returned to the stable state. That in this chapter we wanna speak about this nuclear. When the nuclear, as I say and again say, when the number of proton or neutron is very higher or very lower the number of proton, and this nuclear are in an unstable state, and with decay and emission of some particle can return to the stable state. This nuclear in the physics named radioactive or radionuclide. For example, in hydrogen, deuterium is stable, but tritium is unstable, and with beta emission will go to the stable state. As you can see, deuterium and tritium are isotope to each other, but deuterium is a stable state, is in a stable state, and tritium is unstable state with emitting of beta particle can return to the stable state. It is noticeable to note that nuclear with unstable state, as I say, named and called radioactive nuclear or radionuclear. For example, I can say lead has 6 isotopes, that 3 types of them are radioactive. Okay, up to this slide, only I speak about the how can we have radioactive or radionuclide, and we learn when the number of proton or the number of neutron is very higher than the neutron or proton respectively. The nuclear are in unstable state, and with decay and emission of different particles and gamma rays can return to the stable state. When one radionuclide was to decay, sometimes it happens with one reaction, and sometimes a series of decay can occur until to reach to a stable state. And in the environment, we have two type of the nuclear with radioactivity. Some of them are naturally radioactive, and others called artificial radioactive. As I said, one of them is natural radionuclide that naturally exists in environment, and the other group is artificial radionuclide that creates when a stable nuclear bombardment with nuclear particle and gamma rays go to the unstable state. This process commonly occurs in a nuclear reactor or cyclotron. And it is important to know in the medical and in medical, it's better to say in the medical nuclear, we only use artificial radionuclide, and above the why only we should use radionuclide, artificial radionuclide in medicine. About its reason, I speak in the following. Up to now, only we should know that in the environment we have two types of the radionuclide. That one of them is naturally exists in the environment, and the other is the nuclear with radioactivity that artificially produced in the reactor or in the cyclotron. Okay. As I said, at the first, I want to speak about the main concept of nuclear physics. The main parameter that we should consider in radionuclide agent when we have radionuclide agent is related to decay law and radionuclide activity. At first, we should know when we have, for example, or imagining that you have 1 million of cesium elements with radioactivity. As in the fact, all of them cannot decay in an instance, and decay of this element will occur exponentially. Again, I say imagining you have, for example, 1 million cesium element with radioactivity. I can say all of them cannot decay in an instance, cannot decay in one time, and decay of this element will occur exponentially. So in each time, it is important to know the number of nuclear with radioactivity. Okay, imagining at the time of start time of decay, the number of radionuclide with N0 at time 0, and the number of nuclear that remaining radioactive that have radioactivity after passing time t shown with N. It is important to know how we can calculate the N and or how we can calculate the number of nuclear with radioactivity after passing time t. In this equation, okay, as you see in this equation, the number of nuclear with radioactivity, or it is better to say the differential of number of nuclear with radioactivity is proportional to the number of radioactivity, and we can say the differentiation of or derived of number of nuclear with radioactivity rather than time equal lambda multiply n. And what is the lambda and n? And this equation, n is the number of atoms remaining radioactive, and lambda is the radioactive decay constant. Okay, with solving of this equation, with integration of this equation, we can, at the end, we can calculate the number of nuclear with radioactive after passing time t. As you can see in this equation, the number of nuclear with radioactive after passing time n equal N0 is the number of nuclear radioactive at time 0 multiply exponential of minus lambda t. This equation is very, very important, and please take note of this equation. Okay, other component that is very important after knowing the number of radioactive nuclear after passing time t, the other component is activity. Activity concept is the rate of disintegration of radioactive nuclear, and it is equal lambda, as you can see, it is equal of derived of n rather than time. And as you remember in the previous slide, it can equal to the number of radioactive multiply lambda. And as you can remember, lambda is the radioactive decay constant. Okay, at each time we can calculate the activity that is equal a0, or activity at time 0 multiply exponential of minus lambda t. And in this equation also say exponential of minus lambda t called decay factor. The unit of activity, as say here, is the 1/2 that called becquerel. And the other component that sometimes you are facing with it or see in another book is a specific activity that defined as the activity of a sample divided by its total mass. And on the other word, we can say it's equal activity divided to mass, and its unit also is becquerel per kilogram. The other equation that you should know is this equation, and also you should know the specific. You should know how to can calculate and calculate the specific activity. Okay, up to now we learned how to can calculate the caps lock n and caps lock a, that are the number of radionuclide remaining activity after passing time, and a is the activity after passing time. With knowing the meaning of n and a in each time, I want to introduce the main parameter that is very, very important in nuclear, especially in nuclear protection, and also should be considered, for example, every time you carry a radionuclide drug as a physician. And this is a half-life time of each radionuclide. As the name implies, half-life time is the time that taken for the activity or number of radionuclide to fall to half of its original value. The time that A and N equal the half of A0 and N0 respectively, and as shown in this equation, when the number of nuclear with radioactive time t equals to the half of the number of nuclear with radioactivity at at time 0, the half-life time equal O dot 693 divided by lambda. This equation also is very important. Please take note and memorize it. Up to now, I mentioned three equations that are very important in nuclear medicine. I can summarize them if I can write on the whiteboard. One of them related to N. Sorry. It is too hard, right? on this right one. N equal n0, sorry, multiply exponential minus lambda t activity that's shown with A equal A0 multiply exponential minus lambda t, and the other equation that I say is very important. Why you don't understand anything? Are you talking quickly? Don't you understand? I didn't get your meaning. And half-lifetime that's shown with this symbol. That equal okay, I speak fastly. Okay, I try to speak slowly. Okay. Now I got your meaning. I try to speak slowly. Okay. Okay, and the half-lifetime that equal this equation divided by lambda. This equation is very, very important. Please take note them and memorize them. Okay. Up to now, I speak about the how we can have radioactive nuclear. As you understand, when the number of proton or neutron are very higher than neutron or proton in each nuclear. This nuclear are in an unstable state and with decay and emission of particle and gamma ray can return to the stable state. Okay. And after that, I speak about the main physics concept that we are facing in nuclear medicine. One of them is related to the number of radioactive nuclear after passing T. A is the activity after passing T, and half-lifetime is the time that take to half the nuclear with radioactivity, or to reach to the half of the activity after passing time T. I try to learn them perfectly with getting you some question and some sample question. Okay, go back to our PowerPoint. Okay. But the other component, the other component that is very important when we have a radioactive nuclear is related to biological half-lifetime. And what is it? When the radionuclide is taken to the body, concept of half-lifetime is changed. And not only we have physical half-lifetime, but also we have another item that called biological half-lifetime. Up to now, I speak about the physical half-lifetime. But as this slide shows, when the radionuclide taken into the body, the concept of half-lifetime is changed, and also we have another item that's called biological half-lifetime. In fact, when the radionuclide uptake into the body, various biological processes such as respiration, urination, and defecation are done to the remove drug from the body. The time taken for biological process to remove half of original active material from the body is called biological half-life time. As you remember, physical half-life time is the time that we need to reach to the half of the nuclear with radioactivity, and biological half-life time is the time that taken to remove half of original activity material from the body. To considering the effect of both biological and physical half-life time concepts simultaneously, effective half-life time according below equation is emerged. As you can see, effective half-life time is less than physical half-life time and biological half-life time. As you can see, effective half-life time is equal and the inverse of sum of biological half-life time and physical half-life time. In the following, I get you some question and some question sample that we can better understanding this equation. In this example, you can learn how to use this equation. For example, iodine 131 as a common radio drug that used to label the human serum albumin has a physical half-life time about as I see about 8 days, and the biological its biological half time is 21. In this equation, we wanna calculate the effective half-life time. Again, I return to the whiteboard. In this example, we have physical half-time, that is physical, that is as I remember 8 days. Okay, I say again. Okay, imagining at the time zero you have N0 nuclear that have radioactivity. Okay, and passing time t, the number of nuclear with radioactivity is shown with N. And as we learn, N equal N0 multiply by exponential of minus lambda t. And what is the half-life time? Is the time that N equal N0 equal 1/2 of N0. Okay. Half-life time is the time that the number of radioactivity or nuclear with radioactivity equal the number of equal the half of the nuclear with radioactivity at the start of decay, or is equal the half of the N0. Okay. No. When we say that the the time of when we say that the time of half lifetime for iodine, for example, is 8 days, it means it need 8 days to pass to reach the half of the activity, to reach to get the half of nuclear with activity. Is the time, or in another word, I can say half lifetime is the time we need to reach the half of the activity, to reach the half of the energy. Okay, you understand? Mohammed, you understand my means? Okay, that's very good. Okay, back to our sample question. As I said, the half-lifetime of iodine is about 8 days, and the biological half-lifetime of it is about 21 days. Biological is equal 21 day. Okay, and in this question, we should calculate the effective half-lifetime. So sorry, it is so hard write with mouse. And this based on our equation, half and the effective half-lifetime equal physical half-lifetime plus 1/2 biological half-lifetime. And 1/8 plus 1/21, and with solving of this equation, we can conclude that effective half-lifetime equal 5.8 days. As you can see, the half-lifetime and the effective half-lifetime is lower than physical and biological half-lifetime. Okay? Did you get it, this question? Can I continue? No. Yes, you can. Yes, it's a question. Yes, you're right. And the other sample. Okay, back to our okay, and the other sample. In this example, we want to calculate the total activity of uranium. Naturally, it is interesting to know that naturally uranium consists of 99% of uranium-238 with half-lifetime of 4 to 5 multiplied 10 to the 9 years, and nearly all that 72% of it is uranium 235 with half lifetime of 7 to 30 multiply 10 to the 5 years. And how we can calculate the total activity. Again, as the question say, in uranium, we have two isotopes of them. One of them is uranium 238. That uranium contains nearly 99 to 27 percentage of uranium 238, and other content of uranium is uranium 235. That's uranium nearly contain 0.72% of uranium 235, or in another word, I can say that uranium consists of uranium 238 and uranium 235. That's above 99 to 27 percentage of uranium is uranium 238, and only 0.72 percentage of uranium is uranium 235. And for calculating the activity of uranium as a total activity, I can say that total activity equal A1 plus A2. If uranium has A1 activity, uranium 238, and activity of uranium 235 shown with A2, we can say the total activity equal activity activity of 238 plus activity of 235. Yes? Did you get it this up to now? Can I continue and solve the other part of this sample? Did you get it up to now? Up to now, only I said that uranium consists of uranium 238 and uranium 235, that each of them contain 99 and 0.72 percentage of uranium. Okay, and for calculating the A1 and A2, we learned that A equal lambda multiply N. And in the other equation, we learn lambda equal 930 divided by lambda. And with combining of these two equations, we can reach to this equation that is 93 divided by lambda multiply N. Is it correct? Up to now, I wrote correct. Yes or no? Can I continue? Up to now, it is correct. I wrote correctly or not? Only I can see that Muhammad is active in the class and our other student. Yes, thanks a lot. Thanks a lot for your response. Okay, and the other point that we should know is that 1 mole of uranium has a mass of about 238 kilogram and contain 6.022 multiplied 10 to the 23 atoms. I can say 1 mole, as you remember in chemist, 1 mole of each atom consists of each mass consists 6.022 multiply 10 to the 23. Yes. By combining of these two equations, we can conclude that A equal, sorry, in this equation we should write 1/2 lambda, and it is not correct. Okay, for A1 we can write 1693 divided, and the half-life time of uranium of 238 is equal that is equal 4 to 5 multiply 10 to the 9 years. I can write here, and please pay attention that in time of half-life time should be say in second, and when shown in another unit, we should other unit to the second. Okay. A1 equal n divided by 5 45 multiply 9, that is half-life time in year units, and we should convert to second. For converting, this number should be multiplied to 30, 65 days, multiply 24 hours, and again multiply 60 minutes, and again multiply to 60 seconds. And for N, percentage of uranium was 99 plus multiplied by 6.22 multiply 10 23. Okay, it is very hard to write by this way. I think it is better to back to our PowerPoint and see from the slide. Yes. The main point that you should know here is that uranium consists of uranium 238 and uranium 235. And for calculating the total activity of uranium, at first we should calculate the activity of uranium 238. And we should calculate the activity of uranium 235, and with some of this activity we can reach to the total activity. Okay, and for activity we have this equation that activity equal lambda multiply n, and for lambda we have this equation. With combining of this equation we reach to this equation. This equation is very important to know. If you want, I can say I can write it again. That is, say A equal 6093 and divided half-life time. Okay, you understand how I can reach to this equation? Sorry, Mohammed, do you get it? How I can how I can reach to this equation? This equation is very important. Okay, please take a note, and I try to solve this from PowerPoint, because this whiteboard is not good for writing. I haven't enough space to write it. Okay. 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 As you see in this slide, with knowing activity and half-life time, we can calculate and reach to the activity of uranium 238, and after that we can calculate the uranium 235. Up to now, only you should know how the equation of activity, the equation of number of number of nuclear with activity, and the last is the equation of how to calculate the half-life time. That is equal O dot 693 divided by lambda. Okay, at first, I want to start with the following. As you remember, when the radionuclide start to decay, some particle and radiation are emitted. The main of them are including alpha and beta particle and gamma radiation, and all of these emission change the nature of the nuclear in different way. And also behavior of radionuclides will be changed. In the following, at first we want to familiarize with different particles that emitted and emitted and decay when we have radioactive radionuclide. And after that, we want to know how we can create and produce artificial radionuclide. At first, I want to start with the strongest particle, that name alpha particle. Mostly radionuclide with the proton number greater than lead when the proton number of the one nuclear is upper than 82. This radionuclide can emit alpha particle, and this particle, similar to helium nuclear, contain two protons and two neutrons, and its atom mass is high. That it equal 4. Moreover, due to having two protons, its charge is also high, and it is positive too. Okay, up to now we can conclude that alpha particles have two main properties. One of them is high mass, and the other is high charge. And because of having high charge and high mass, it has specific properties that I speak about them in the following slide. In the below equation, as you can see, we have a mother radionuclide that decay to the daughter radionuclide, and beside them we have alpha particle that sometimes shown with helium nuclear. You can see a radionuclide emit alpha particle. When alpha particle is emitted, you can find the proton number and atomic mass in daughter nuclear are 2 and 4 units less than mother nucleus respectively. As you can see, radium is the mother radionuclide here, and the atomic number of radium is 88, but atomic number of argon is about 86. And as you can see, the proton number in daughter is 2 units less than atomic number in mother radionuclide. And when we comparing the atomic mass between radium and radon as a mother and daughter radionuclide, we can understand the atomic mass of radon is 4 units less than mother radionuclide is 4 units less than radium. Yes. And because we have alpha particle that has 2 proton and 2 neutron, or we can say alpha particle that the atomic mass is 4 and the proton number is 2. It is important to know in each nuclear reaction we have 3 conservation. One of them is a mass conservation. As you can see, the mass number in the left side of the equation is 226, and in right equation is equal 222 plus 4. And as you calculate, the atomic mass in the left and right side of the equation is equal. And the other component that should be conserved is energy and charge. Because in daughter we losing 2 proton, we losing 2 number of proton. Alpha particle has positive 2 charge. And with calculating and comparing the right and left side of the equation, we can understand the charge of two sides of the equation is also equal. Okay. For the other particle I want to speak about it is beta. For beta particle emission, we have another story. When the number of neutron is over than proton, a neutron decay into the proton, and like kind of this reaction, an electron is created to maintain charge conservation. Again, I say when the number of neutron is higher than the proton, with converting the neutron to the proton, electron with minus charge with 1 unit with minus unit can be created. This electron with negative or minus charge named beta particle. As you see in this equation, with when neutron converted to proton, an electron particle is produced. Again, I say when we have a radionuclide nuclear, and that the number of neutron is higher than the number of proton, and one neutron converted to the proton, and beside this an electron particle is produced. This electron particle named beta particle. In addition, in this equation, you can see another particle that's shown with this symbol, and this is named antineutrino. This is the antiparticle to the neutrino, and it carry away some of the energy of the disintegration, of the decay. In fact, when we have in fact, we can say antineutrino is produced to maintain energy conservation between two sides of the equation. It has no charge and no mass, and just created to conserving the energy. It is important to know in each disintegration, again, I say there are three rules that should be happen. One of them is conservation of charge, other is conservation of the mass, and the last is the conservation of energy. Perhaps ask from you why attenuation produce line-side beta particle. You should reply due to maintaining the energy conservation. Sometimes in the exam ask from you why we have antineutrino beside the beta particle, and you should answer to maintaining the energy conservation, and antineutrino particle should be produced. Okay, the next particle that I want to speak about it is positron. As you see, positive beta or positron particle is emitted from an element which have a high proton compared to neutron. As you remember, for beta emission, I say when we have a radionuclide that its neutron is very higher than the proton, with emitting beta particle, it can return to the stable state. But for positron emission, it is vice versa. When we have a radionuclide that the proton that its proton number is higher than the neutron, we can have a positron particle. Due to decay of proton to neutron, or due to converting of one proton to neutron, a positive charged electron called positron is created. Again, here we can neutrino to maintain the energy conservation. And it is important to know in positron emission, we have radionuclide that the number of proton is very higher than the number of proton, and with converting of one proton to neutron, we can have a positive beta or positron particle. And the last is gamma ray. It is important to know that gamma is not a particle, have no charge and have no mass, and is a photon with a specific wavelength. Gamma ray, which is not, as I say, which is not particle, and as you know, is electromagnetic radiation that are emitted from the radionuclide following beta or alpha emission. When daughter nuclear are left in metastable or excited state, for example, for technetium that is in metastability state, with decay and emission of gamma radiation can return to the stable state. Usually, this occur immediately after the main decay. Sometimes the daughter can exist in a metastable state for, and sometimes delay and when nuclear are in a stable state with emitting the gamma ray can return to the stable state. Please pay attention that gamma radiation can be occur in two situations. Immediately after the main decay beside alpha and beta and positron emitter, and also when daughter radionuclide are left in a metastable state. In metastable state, the only emission is gamma radiation. Again, I can summarize all of the things that I said in this slide. As I said, in the environment, we have three types of state for nuclear. One of them is unstable. One of them is unstable state. Other is metastable. Or semi-stable. Metastable. Sorry, my handwriting is not very bad, but it is hard to write in by this way. Unstable, metastable, and stable. Stable. Okay. When we have nuclear that are in unstable state, and they are named radioactive. Yes, radioactive. They are said radioactive. Okay. Sometimes radioactive nuclear can directly decay to the stable state. In this situation, they emit alpha, positive beta, or negative beta particle alongside gamma radiation. Okay, gamma radiation. Okay. But sometimes, at first, unstable state, unstable radionuclide that are in the unstable state at first go to the metastable with emitting, for example, alpha, positive beta, and negative beta, and then with emitting the gamma radiation can return to the stable state, can return to the stable state from the metastable. Okay, as you see, we can, as you can see, gamma radiation can be occur in two situations. No, because I understand your words. Okay, that's very good. The main point is that gamma radiation can be occur in two situations. Immediately after the main decay, as you can see by this reaction, and sometimes at first daughter radionuclide go to the metastable and left in the metastable, and in metastable the only emission that occur to return to the stable is gamma radiation. When we have, it is important to know when we have a radioactive that are left in the metastable, only with emitting the gamma radiation can return to the stable. But when we are in the unstable state, we can emit alpha, positive beta, and negative beta. But when we are in the metastable, or we are left in the metastable, only with emitting the gamma radiation can return to the stable state. Okay, did you get it, this point? Difference reaction that occur between the unstable state to a stable, or from the meta-stable to stable. That's very good. Okay, and the last reaction that's for the end of this section I wanna teach you is electron capture. Okay, electron capture is Electron capture is another interaction that occurs in radionuclide emission. As you remember, when the number of proton is over than the neutron, I say that in this radionuclide we have positive beta or positron emission. But when the differences between energy level of mother and daughter is lower than 1 to 2 mega electron volt, decay of mother radionuclide cannot accomplish with positron emission, and instead of it we have electron capture. As you remember, in positron emission, when we have radionuclide that its proton number is higher than the neutron number, with converting one proton to neutron, we have a positive proton, positive beta or positron. But there is some exception. When the difference between energy level of mother and daughter is lower than 1 to 2 mega electron volt, decay of mother radionuclide cannot accomplish what a positron emission, and in this situation we have electron capture. Same as positive beta decay, in electron capture, the number of atomic mass is left unchanged, and the number of proton is reduced by 1. In fact, in this reaction, one electron from inner layer captured into the nuclear and combined with a proton to produce a neutron. And due to losing an electron from inner layer, subsequently an electron will move from an outer orbit to fill the space left by the, for example, k electron, and so in this situation the characteristic X-ray photon is also emitted. I can say the electron capture is one of the nuclear reaction that we have that accomplish with X-ray photon emission. And again, for more explanation, I write them on the whiteboard. When proton number is higher than neutron number and the difference energy is upper than 100.022 mega electron volt, we have positive beta. Okay, but when proton number is upper than neutron number, but energy between two level of mother and daughter is lower than 1.022, we have electron capture. Okay, electron capture. Okay, in this situation, again, I say an electron from inner layer capture into the nuclear and combine with proton to convert a neutron or to produce a neutron. Due to losing an electron from inner layer, as you can see, when we have a, for example, this is my nuclear, and this is electron orbital around it. When electron captured to the nuclear and with combining of electron with proton and a neutron can be produced. When electron enter to the nuclear, we have a hole or vacancy in electron orbital that in this situation an electron from upper layer, for example from this place, will move to the space left by the electron, and in this situation we have X-ray, as you learn in radiology chapter. Yes, X-ray. Okay. Again, I say it is important to know in nuclear interaction we have to mention that line size, then X-ray also are produced. One of them is electron chapter, or we can say the electron chapter is the one of the nuclear reaction that accomplish with X-ray emission. Okay, up to now I speak about the main particle and rays that emitted after having a nuclear with radioactivity. I see we can finish the first section, and if you are agree and if it doesn't matter, we can continue the next section for the, I think, for the 10 minutes later. Yes, 10 or 15 minutes later. Yes, that's very good. Okay, the next section will be a start at 10 minutes later or at 5 minutes later. Sorry, at 15 minutes later. Okay, bye for now. Okay, are you there? Hope you are not tired, and if you are ready, I start the next session. Yes, thanks a lot. I share my screen. In the last session, I speak up to 20 slides. Yes. Okay, up to now, in the last session, I speak about the different and main particle and rays that will be emitted and decay when we have a radionuclide, and when radionuclide one return from unstable state to the stable state. In this slide, you can see the comparative properties of nuclear radiation. As you can see, the charge and mass of alpha particle is is the highest among the different particles. Mostly alpha particle, alpha particle interact with the orbital electrons. Beta particle interact with the electrons, eject electron, produce some secondary ionization. And as you remember and you learn in radiology chapter, when we have X and gamma rays, this electromagnetic rays can interact with the electron and can induce photoelectric compound and pair reaction. Okay, in the following, we want to know the penetration rate of different particles in tissue. As as far as you remember, up to now, we familiarize with alpha, positive beta, and negative beta, and gamma and X rays that can emitted through nuclear interaction. And the main point about them that we should learn is the penetration rate of them. When one particle interact with a target, the absorbed energy cause some ionization and excitation, which can result in chemical changes alongside a variety of biochemical effects. The main point in the amount of absorbed energy in tissue is quite different between each type of the radio activity. For example, when we have alpha particle, the absorbed energy of it is completely different with when we have positive beta particle. Or on the other word, we can say the amount of absorption energy of this particle depends on the type of the article and its energy. So in the following, we want to know these differences, and we want to know the main parameter that determine the depth of particle into the target. And we want to know which parameter determine the penetration rate of different particles that we learned up to now. Okay. Again, we start with alpha particle. The high mass and high charge of an alpha particle relative to the other form of the nuclear reaction give this particle greater ionization power. So this particle easily can interact with the first target and deposit nearly all of their energy and finally will be stopped. So we can conclude that penetration rate of this particle is very, very low. Or on the other word, it has the porous ability to penetrate different matter. Again, I say the lowest penetration rate or smallest pore is belong to the alpha particle because it has high charge and high mass, and it is better to say it has the smallest pore because this particle easily can interact with the different target with electron and nuclear of the different atoms and easily can deposit nearly all of its energy to the target. So the penetration rate of this particle is very, very low because this particle deposit of its energy in a very, very small distance. When alpha particle interact with tissue, it will be observed by for example, as you can see in this slide, by a micrometer of skin. So when if we compare beta particle with alpha particle, we can conclude the charge and mass of beta particle is very, very lower than the alpha particle. So the interaction of beta particle rather than alpha particle is very, very low, and we can conclude that penetration rate of beta particle is higher than alpha particle. The main point is that the maximum depth is considerably greater than alpha particle. Up to now, we learned that the lowest board is belong to the alpha particle, and after that is belong to the beta particle, and the board of or penetration rate of beta particle is higher than the alpha particle. Okay, their radiation, the other radiation that we are facing when we have radioactivity nuclear is gamma rays. As I said before, gamma ray is not a particle, so has no mass and no charge, and its interaction with targets is completely different with alpha and beta particle. As far as you remember, the most important of gamma rays interaction with tissue are including photoelectric compound and pair and production of pair. And for gamma rays, we don't have a defined penetration depth. And we can conclude that gamma has an exponential attenuation such as X-ray. As other electromagnetic radiation, the attenuation of gamma rays in tissue is proportional to the inverse of square law. You can see in this equation, you can see the intensity of gamma rays after passing our distance equal the intensity of gamma rays at r0 distance to the tube. And that based of this equation, we can conclude the intensity of gamma rays is proportional to the inverse square law. Okay. And the other particle that is important in nuclear decay is neutron. It can be emitted spontaneously in the fission of uranium-235 that I say about it in the following, or emitted as a result of bombarding the nuclear with energetic particle. Neutron with energy lower than 1 mega electron volt are called fast neutron, which can collide with several nuclei and cause considerable ionization before a stop. Okay, up to now, I can summarize what I say in this slide. I speak about the penetration rate that is different between different particle and rays. Alpha, due to has high mass and high charge, has the lowest penetration rate and can nearly deposit all of the energy in a very, very small distance. It can stop with a piece of paper, and the board of it can be nearly micrometer. And the particle that is very important for us is a beta particle. That, as you remember, I said due to irregular paths, the depths cannot be accurately defined, but we can conclude that the distance of beta particle or penetration distance of beta particle is higher than the alpha particle. And the other rays that is important for us is gamma, that I said haven't defined penetration depths and different and change based on its energy. And I say the attenuation of gamma ray is exponentially to square law. Is proportional to the square law, is exponentially and proportional to the square law. And again, I said intensity is proportional to the inverse square law. That is very important. We can conclude up to now that the penetration of gamma is higher than the beta, and beta is higher than the alpha. Okay? Do you understand up to now? Do you understand the difference between the penetration rate of alpha, beta, and gamma? Yes, that's very good. In the following, as I said before, radioisotope can be produced naturally and artificially because half time of natural radionuclide is very high. For example, for radium, the half of time and its half lifetime is about 1,600 years. At the medicine, it is not possible to use this radionuclide because their half lifetime is very hard. Inevitably, we must use artificial radioisotope. Today, we have more than 2,000 type of the artificial radioisotope that in the following we want to know how can we create and produce different radioisotopes. We use generally we use two methods for production of artificial radionuclide, and that are including nuclear reactor, and the other method is related to cyclotron. I'm going to speak about them in detail. It is important to know none of 2,000 artificial radionuclides that are created and produced in nuclear reactor or cyclotron are practical and useful for using and applying them as right. There are many factors that should be considered for them, and in following I also mention to this factor. I start with the main method to create and produce artificial radionuclide, that is nuclear reactor production. When nuclear with a very high mass such as natural uranium observe neutron instead of produce radionuclide with a higher mass, split to some radionuclide with a smaller mass, so that the sum of the mass of daughter radionuclide nearly equal with the mother radionuclide. Besides this, we again have produced neutron and release of energy. And the other important point is that produced radionuclide here is nearly pure, and the important radionuclide produced by fission are molybdenum-99 and iodine-131. It is important to know in the nuclear reactor we have different reactions that help us to produce artificial radionuclide. One of them is fission reactor. In the fission reactor, as I say, nuclear with very high mass, for example, uranium, observe neutron, and instead of radionuclide, instead of producing radionuclide with higher mass, split to some radionuclide with a smaller mass. And as you can see, the proton number of mother nuclear is different to the radioactive is different with the created radioactive daughter that are barium and krypton. As you can see, the proton number of uranium is different to the proton number of barium and krypton. Yes. In this situation, when we produce radioactive daughter from the stable nuclear mother, we take simple chemical reaction, separate the produced radioactive daughter from the nuclear. From this, by this reaction, we can That is very, very important for us. As I say, reaction, we have a large number of useful isotopes that can be used as radiodrugs, such as iodine and molybdenum that I say in the last slide. And typically, these produce radiodrug emitted beta particles that are very proper for that are very useful in therapeutic aid. Again, I mentioned some important points regarding to fission reaction. As you learn in fission reaction, we can produce radiodirect daughter with because the atomic number of daughter is different to the number of mother nuclear, and we easily separate them from the mother with a chemical process. And the other point about the fission is that in fission reaction typically we can create a radiodirect daughter that emits a beta particle. Two main points about the fission reaction. One of them is related to high purity of radioactive daughter, and the other is related to the emission of them that typically they emit a beta particle. And as I say, in reactor we have another reaction that help us to produce radionuclides. In reactor we have another reaction which are categorized in three groups. The first in N and gamma reactor. Or neutron capture reaction. It happens when a nucleus irradiated with neutron and capture neutron and emit gamma rays. For example, 31 phosphate is irradiated with neutron and then emitted gamma radiation. As you can see in this situation, when you compare the created radioactive daughter with the mother nucleus, you can find that the proton number of the mother is equal proton number of mother equal to the daughter. And in this situation, we cannot easily separate the produced radioactive daughter from the mother, and in this situation created or produced radioactive daughter is not chemically pure. That is very important, and for medicine only we can artificial radio active nuclear that have high purity, high chemical purity. And the other event that can be occur when nuclear captured neutron is proton emission. Reactions are less common and require higher neutron energy than proton is ejected from the nucleus as a result of the absorption of neutron. The main properties of production of radiodirect by this way is spherical produces radiodirect same as fission. As you can see, with capturing a neutron to the nucleus and producing and ejecting one proton, the proton number of producer radioactive daughter is different with the proton number of mother. And in this situation, we can easily, again I say, we can easily separate the producer radioactive daughter from the mother. And in this situation, we can produce high chemical purity radioactive. And important example of this is the production of carbon 11 from nitrogen for use as a labeling tracer of organic molecules in biological and medical research. And the last reaction can be occur when one nuclide is irradiated with neutron is alpha emitter. And the only important medical example is the production of tritium, an isotope of hydrogen from lithium. And you can see again in this reaction we have produced radioactive daughter with high chemical purity because the atomic number of helium is different with the atomic number of lithium, and we can easily separate the helium from the lithium. Okay, up to now I speak about the different reactions that occur in reactor and help us to produce different radioactive daughter that some of them has high chemical purity, such as fission reaction, NNP and NN alpha reaction that help us to produce radioactive daughter with high chemical purity. Okay. And the other way that we can produce radionuclide is by cyclotron. In cyclotron, in spite of the reactor, we bombard the nuclear with a charged particle. It is the main differences. Please pay attention. The main differences that happen between reactor reaction and cyclotron is related to the particle that interact with the nuclear. In the reactor, it is better to say that we bombard our nuclear with uncharged particle, with neutron particle, but in cyclotron, we bombard the nuclear with a charged particle, sometimes with alpha and sometimes with proton particle. Is the first difference between the cyclotron and reactor reaction. As you see, when, for example, the charged particle that are usually used in cyclotron is neutron and alpha particle, and as you can see, when nitrogen is in a stable state, is bombarded with alpha particle or with neutron, can produce oxygen radionuclide. Same as fission, in cyclotron, produced radionuclide daughter has a chemical purity. That is very, very, very important. It is important to know in medical. Again, I say in medical, we should use radionuclide with short half-life time and with high chemical purity. Okay, do you understand the main difference between the cyclotron and reactor? Yes or not? Yes, that's very good. Again, here said that producer radionuclide is cyclotron has chemical purity such as fission reactions, such as in an alpha in an proton reaction that occurred in the reactor. And the last method to generating and creating the artificial radionuclide is generator method. It is important to know, again, I say it is important to know in medical we should use radionuclide with very short half lifetime as we can. So we need on-site reactor or cyclotron near to the hospital to produce and create radionuclide. And as you know, it is not practical. We cannot have a reactor or cyclotron site near the hospital. Generator for solving this problem, generator were created. In fact, generator enable us to produce radionuclide with very short half-life time without need for an on-site reactor or cyclotron. Again, I say and mention to the necessity of generator. Generator enable us to produce radionuclide with short half-life time without need for an on-site reactor or cyclotron, without having a reactor or cyclotron near our hospital. For this aim, the interested radio-derived data should have short half-life time, and modern radionuclides should have long half-life time. For example, we want to produce technetium-99 in metastable state as a radio-derived data, and radioactive nuclear that can produce this data is molybdenum-99. The first step that we should consider is that the half-lifetime of the mother radionuclide should be very higher than the half-lifetime of the daughter radionuclide. It is interestingly that the separation of daughter from the mother in generator called milking. And the common radiodrag that produced by this way, as I say, is technetium-99 in metastable state. And as you see, mother radionuclide is molybdenum-99 has high half-life time is about 67 hours, but the half-life time of the technetium is nearly, as I say true, is nearly 6 hours. And when comparing the half-life time of the mother with the half-life time of the daughter, you can understand the half-life time of the mother is very higher than the half-life time of the half-life time of the daughter. 67 is very higher than the 6, and it's nearly 10 times. We can say the half-life time of the daughter is nearly 10 times shorter than the mother. Okay, as I said, technetium is metastable state in common radiodrag that produced in generator, and in the following we want to know how. Mother radionuclide means molybdenum is obtained from a nuclear reactor either by, for example, in a fission reaction. When we bombard uranium with a neutron, we can produce molybdenum. We can say molybdenum is prepared in this form of reaction by fission reaction in a reactor. Molybdenum is prepared in form of the ammonium molybdenum and absorbed on the aluminum and a glass or plastic column. Uh, in column of generator, when a solid solution is passed through the column, easily created radioactive daughter that here is technetium-99 in metastability can easily separate it from the molybdenum, and this process named milking. Okay, and in this figure, you can see the process of separation of technetium from molybdenum. It is valuable to know in each generator we can milk in technetium-99 for 4 times. After that, the new generator should be replaced. There are in this slide there are some important points that please pay attention to them. As said in this slide, radionuclide generators are devices or methods that produce a useful, short-lived medical radionuclide, known as daughter, as I said in the last slide, from the radioactive transformation of a non-medical line-like radionuclide called parent or mother. As I said, in medical imaging, in medical nuclear, especially in for imaging aim, we need radionuclide with a very short life, with a very short half lifetime. And for this aim, we can produce them in the generator. As I say, a technetium-99 generator or is a common radionuclide that's used in nuclear medicine, and a generator that produces this radionuclide called technetium-1990M generator. As said in this slide, it is a device used to extract the metastable isotope 1990M technetium from a source of decaying molybdenum. Molybdenum-99 used in this generator is produced either by neutron irradiation or by fission, as I said, and to choose fission reaction, because in fission reaction we can produce molybdenum with high chemical purity. As a pattern, molybdenum-99 decays, the concentration of daughter technetium-1990M increase in the column. As you can see, when the molybdenum are decaying, the concentration of the technetium-1990M is increasing. Technetium-1990M reached a maximum after about 5 times of its half-lifetime. It is very, very important point that try to memorize it. Or in the other words, I can say when we have a daughter and a mother in a generator, the maximum concentration of the daughter reach after about 5 times of its half-lifetime. And because the half-lifetime of technetium is about 6 hours, we can conclude that the maximum amount of technetium-1990M in generator is obtained about 4 multiplied to 6. That is equal 24 hours. Or in the other words, we can say in this case, when we have technetium-1990M, the maximum amount of 1990 technetium obtained after 24 hours after the first milking. Or sometimes ask from you, for example, in your exam, imagining we have a daughter in a generator with half-lifetime of about 8 hours. Which time we can obtain the highest amount of this daughter radionuclide? Can you answer me? Do you get the question? Okay, again, I repeat it. Imagining you have one generator. In a generator, you have a parent and daughter nuclear. Yes. If there is about 8 hours, in which time you can obtain the maximum level of your daughter. As in this slide say, it is about 4 times of its half lifetime to reach the maximum amount of data. And if you know the half lifetime of the data is about 8 hours, in which time we can obtain the highest level of the data. It is illustrated in this slide. Please pay attention. Didn't get it? Mohammed, I'm waiting. I'm waiting to hear your response. Yes. Okay. I explain it again. No, 48. No, 4 multiply 8 is 32. Again, I say in the whiteboard, I say we need 4 times of half lifetime to reach maximum amount of daughter radioactive. Okay, and if we can summarize this equation, 4 multiply half lifetime. Okay, if half lifetime equal 8 hours, we can conclude 4 multiply 8, that is 32 hours to reach the maximum amount of produced radio drug data. Yes? You understand? Yes, thanks a lot. Okay, I think it is our time is over, and it is better to finish our subject up to this slide. Yes, do you agree with me? Okay, you can ask your question, and also you can send your question to me through email. If you wanna, I can share my email address to all of you. An exam will be the same day if every subject is a day. Sorry, I didn't your mean. My exam, my question exam is from this slide, and I think if you read this slide, all of the subject is very is not very hard for you. I think it is hard for you because all of this is new for you. Yes. Yes, I sent my email address, that is z_arab @yahoo.com. Okay, and I will send this PowerPoint, and if you want the record of this class to you. Yes, I send my PDF and my PowerPoint to you. And if you want my if you wanna record of this class, I also send to you. Tell me you want or not. PDF is enough for you. PDF of this presentation enough for you. Yes. Okay. Send me your email address that I share PDF with you. I'm waiting to